Welcome everyone to my talk on extreme algorithm selection with dyadic feature representation. My name is Alexander Tornede and this is joint work with Marcel, Wever and Eyke Hüllermeier, and we are all from Paderborn University in Germany. So let's start with the first part of the title, as I assume not everyone here is familiar with algorithm selection. We'll start with talking about what algorithm selection actually is and then come to what extreme algorithm selection is indeed and where we think a dyadic feature representation is the right way to tackle that problem. Okay, so let's start with algorithm selection. We have a set of instances of an algorithmic problem that could be anything, for example, the Boolean satisfiability problem, the traveling salesman problem, or even just classification and machine learning, yeah? And then you have different instances of these problems, for example, different set instances, yeah? And you also have a set of heterogeneous algorithms which basically can solve this problem or instances from this problem. For example, in the case of SAT, this could be SAT solvers. Yeah? And then the goal is to learn a mapping from this instance space to the algorithm space. And this mapping should be done in such a way that for a given new instance, you want to choose the algorithm which is optimal with respect to some measure m, yeah, that maps from the joint space of the two, for example, to the real numbers in the easiest case. Yeah? And this measure is usually some kind of performance, in the sense that, for example, it could be in the case of classification a loss function such as accuracy, or in the case of SAT solvers you're usually interested in runtime, yeah, because you want to have the algorithm that solves the instance fastest. Okay, so how is this done? So of course the easy solution would be if we're given a new instance, yeah, select the algorithm that simply maximizes this MAI, so our performance measure. Yeah, this would be the easiest approach, of course. Unfortunately, this exhaustive iteration over a set of algorithms doesn't work because we assume this M to be costly to evaluate, which means that we just cannot iterate through the whole set of A and evaluate that for each algorithm, which also makes sense because if you think about it, for example, if you're interested in finding the algorithm that's probably fastest on a new Z instance, you don't want to run all of them because then in the end the whole selection problem doesn't make any sense. What's the real solution then instead? The real solution is that you try to learn a surrogate of this original measure M, yeah, so this M hat, which basically has the same form. However, it has the nice property that it's actually cheap to evaluate. And by the time you have this property, of course, this exhaustive iteration that wasn't possible before is now possible. And this is exactly then what is done. And there are lots of methods out there that all work in one way or the other like this. There are some exceptions, but then generally this is the scheme. They mainly differ in what kind of hat they learn, so to speak. And the key thing here in order to be able to do that is that we assume that we can represent instances by features. So for example, for a Z instance, this could be something like the number of clauses or the number of variables, whatever, basically gives the selector information regarding which algorithm might work best on that instance. So a simple example of the scheme can be found in something that's called Zatzilla07. That's a very common algorithm selector for Z instances. It's from the year 2007. And basically what they do is they learn such a surrogate model for each of the algorithms separately, yeah, which just maps from the instance to the real numbers and then basically estimates the performance of the algorithm, for example, A1 on an instance in terms of the measure M. And then, of course, you can just redefine this joint surrogate model, which we have here on this algorithm-wise models we have on the left. And that's basically what's done. Just that you have an example how this is done. There are other things, for example, there are other methods which learn such a surrogate model per pair of algorithms and then compare things and so on and so forth, but that's just a small example here. What's extreme algorithm selection and why do we think that a dyadic feature representation actually makes sense? So the general scheme of extreme algorithm selection now is still the same as an algorithm selection. The only difference here is that the number of algorithms we can choose from is now extremely large, but still finite. That's an important point. And that has several implications, so to speak, which we'll come to in a second. So let's look at this in comparison to some other problems. So you already know algorithm selection now, yeah? And we also compare against algorithm configuration. That's pretty similar, except that you don't have a finite algorithm set, but you actually try to configure an algorithm, and hence your configuration space is usually infinite, because by the time you have a real value parameter, of course, you can have infinitely many configurations. Yeah? And if we basically compare these different settings on two scales, namely the response time, so in how much time are you allowed to take before you need to return an answer, and the number of candidate solutions, so from how many alternatives you can choose. And if you basically take a look at these problems on such scales, then you can see that in algorithm selection, we usually assume we have a pretty limited number of algorithms to choose from. Yeah, that's usually in the tens. It's kind of a hidden assumption that's usually there. However, you want a more or less instantaneous answer when you ask someone, when you ask the selector what kind of algorithm works best on this instance. That's different for algorithm configuration. Yeah, as already mentioned, the number of solution candidates is possibly infinite, but you also have a lot more response time due to this, because you assume that you can do cost-line online evaluations. And the setting of extreme algorithm selection that we suggest with this work is somewhat in between. Yeah, so we assume that we have an extremely large set of algorithms, so thousands or even tens of thousands or more, but it's still finite. However, we cannot really afford the cost-line online evaluations as an algorithm configurations, because we want an answer more or less instantaneously. Okay. And then if you take a look at these things, there are also some conditions that change with respect to the training data. Because if you think about algorithm selection, what you usually assume is that you have some training instances where you can train your selector on. Yeah. And for these training instances, you usually also assume that more or less for most of the algorithms, you have a value on how good they performed on this instance with respect to your measure. For algorithm configuration, in contrast, you usually assume to have no training data at all, but I mean, you can do the costly online evaluation, so it's not that much of a problem. And thus, things are a little bit different in the sense that we still assume that we have training data as an algorithm selection. However, this training data is not really dense anymore, and this is also reasonable, because if you think about it, if you have a couple of thousand algorithms, you cannot reasonably assume that someone ran all of these algorithms on all of your training instances anymore. Yeah, but rather that you have only a couple of evaluations per instance, which also means that for some algorithms you might not have any evaluation at all, which is of course unfortunate, but in principle it can happen. So how does it look? So, right, in principle, our training information then looks like kind of this table here. On the left we have instances with features that represent the instances, and we have the algorithms on the top, and then we have in the entries basically the performance of the algorithm on the corresponding instance with respect to our measure. Now, if we have extremely many algorithms, as we have here, for example, 1,000 for just example purposes, then learning a model for each algorithm, or maybe even pair of algorithms, simply doesn't scale anymore. Because first of all, you need an extremely large amount of models now, namely 1,000, right? But what's even worse is that these the models that you want to train for these algorithms just don't have much data anymore. For example, if you compare it here, there's some algorithms with one sample, most of them actually, and you cannot reasonably infer a model from one or even a handful of samples, right? You will have really bad models in a sense. And for some algorithms, we also have no evaluations at all, which means that you cannot train any model at all now, right? And that's of course not what you want to have here anymore. So now, what's our suggestion? As the title of the slide already suggests, we assume that this, or we hope that this dyadic feature representation actually solves this problem, the following sense. Now what we do is we also represent the algorithms by features, So if you look at this table on the left, this means that we actually now get features for the columns as well. Now, that of course assumes that we also have a feature function for the algorithms and not only for the instances that somehow represents the algorithms in terms of meaningful features. Now, the cool thing about this idea is that now it allows us to learn a joint model across instances and algorithms, and we don't have to learn a model per algorithm anymore, which also means we can much better use the training data. So actually in detail, you may wonder why this is called the dyadic feature representation, and the reason is because we denote the tuple of these two different feature vectors, instant and algorithm, as a dyad, because it's like, it has two elements. And the advantages of this feature representation are, as I already said, you can learn one model instead of many, and you have a lot more data for the data set for the single model available, which is of course, which means that you can use this data in a better way. And another cool thing is that you can actually make predictions about algorithms you have never seen, right? As long as we can represent them in terms of a feature vector, we can make predictions about them because we have a way to represent it. However, we induce another problem here, namely how to combine these features to learn a joint model. Yeah, the easiest way would be a concatenation, but of course you can think about more complicated ways. And the way we suggest to do it is to model this combination of features via a so-called feature map phi. Yeah, that could be, for example, parameterized with a weight vector, which then tells you how to combine these features for any model that you want to learn in the end. And we suggest two ways to do that. So the first one is just the simple concatenation, as already mentioned. However, it turns out this is actually a pretty reasonable approach in terms of performance. It works quite well, as we'll see later on. And then if you use the simple concatenation, you can just learn any regression model on these concatenated feature vectors. The other approach that we suggest is to learn this feature map implicitly via a neural network by basically feeding these in the form of a simple concatenation in, and then let the neural network decide on how it wants to combine the features essentially during the training process. And we also suggest another kind of model, except for doing this, just for illustrative purposes, we don't do a regression model here, but we actually use a ranking model that's then able to generate rankings over algorithms, and then we just pick the best one that's suggested by the ranking when we have a new instance. Okay, so the third contribution of our paper was a benchmark for this new problem that we suggested. And let's see how this looks. Yeah, so the algorithmic problem we're looking at is the problem of classification, which means that we have simple classification data sets as instances. And the set of algorithms is made up in the following way. We took various parameterizations of different classification algorithms and then considered each of these parameterizations as a distinctive algorithm. Yeah, which means that we end up with over 1,200 total algorithms. And then we considered different fill rates of the training data available. So fill rates with respect to this training matrix that I already talked about. Yeah, because recap that you usually cannot assume that this matrix is reasonably completely filled, but it's rather probably really sparsely filled. So we assume different fill rates. Now 4% here means that basically for each instance we assume that 4% of the available entries are filled on average. So that at least for each instance you have some kind of reasonable assessment, so to speak. Now, in terms of feature representations, we decided to do the following. So for the dataset, we use 45 OpenML landmarking meta features. Landmarking meta features are basically, or you can think of it as basically performances of easy to or fast to evaluate learners on the dataset, or maybe a subset thereof if the dataset is really, really large. The limitation of this kind of representation is that it's not very fast to compute, because in the end you need to run a learning algorithm on it and evaluate it, right? So for the algorithms, we use a different feature representation, because as you can imagine, there's simply not so much out there. And we do it in the following way. So basically we exploit the fact that we're actually looking at configurations of algorithms here in the following sense. So the feature vector for an algorithm contains one binary feature indicating which algorithm we're actually currently looking at. Yeah, and then one feature per parameter that either takes the value of the parameter or a 0. Yeah, so for example here, if we have algorithm A3, and this could be, for example, a support vector machine, then this one would mean that it's indeed a support vector machine, and then following all of the parameters of the support vector machine that we can select would come. Yeah, and the 0, for example, would indicate that it's not a KNN, and then you just set all of the parameters that belong to the KNN to 0. Yeah, and if we want to encode then all the categorical parameters, we end up with 153 features in total. However, this representation has a limitation because so earlier I talked about the advantage of being able to scale to unknown algorithms. That doesn't work here anymore, right? Because then you would need to extend the feature vector. Okay, let's have a look at the results. So what we're looking at here is the so-called regret at k. That's nothing else than the difference between the best algorithm in terms of accuracy and the best algorithm in the top k algorithms returned. Yeah, and we're comparing against 3 different approaches. The per algorithm regressor here is just the model from the very beginning, where you learn a single model per algorithm, and these are 2 collaborative filtering variants. And these 2 are our approaches. The left one is the ranking one, and the right one is the regression approach. And we're looking at different fill rates that we talked about earlier here. And as you can see, our approaches perform clearly superior in comparison to all of the baseline approaches, which means that apparently this dyadic feature representation is actually helpful here and allows the approaches to scale across this large number of algorithms. Now, let's end the presentation with 3 take-home messages. So what did we learn today? We introduced the setting of extreme algorithm selection, where you have extremely many algorithms to select from, but you also have this need for instantaneous recommendation, which means that standard algorithms simply do not scale anymore. However, the dyadic feature representation that we introduced here allows these approaches to be able to scale and clearly perform superior to the other approaches. So all code, experiments, and also the benchmark dataset can be found on GitHub. It's publicly available under this link or also under this QR code. So thank you for listening to the presentation. If you have any questions, feel free to contact me.